Hello, Gen Chem students. As promised, here is your problem that's going to feature a dilution and a percent ionization calculation. We begin with a 3 molar solution of aqueous ammonia. We dilute this solution to 0.1 molar. We want to know what is the new percent ionization. We've been given the Kb of ammonia, which is 5.29 times 10 to the negative fifth. This requires two major steps in our calculations. One, we're going to use an ice table to get the hydroxide concentration, and then we're going to use that hydroxide concentration to get the percent ionization. These are two types of calculations you've been able to practice a lot in class, so let's just put them together. So first off, we're going to write out the process that's going on. We've got aqueous ammonia in water, reversibly becoming ammonium, NH4+, which is aqueous, plus hydroxide, which is also aqueous. This means that our mass action expression, so the equilibrium expression for this base process, is going to equal that 5.29 times 10 to the minus fifth, and the terms are the concentration of ammonium times the concentration of hydroxide over the concentration of ammonia. Now that we have these, we can write out our ice table and crunch our numbers. So we're going to start with the reaction in question. Ammonia reversibly becoming ammonium and hydroxide. Our initial condition. So we've diluted to 0.1 molar. This is our new initial concentration, 0.100 molar, and there's no ammonium or hydroxide initially. Our change, the ammonia is going to have to reduce by minus x because we're going to increase both the ammonium and the hydroxide by plus x. And in this case, we cannot assume that the base concentration will stay constant. There's no reservoir of extra base to replenish it. The 0.1 molar is all we have. Therefore, our equilibrium values will be 0.1 minus x for the ammonia, and x for the ammonium and the hydroxide. We're going to take these and plug them into our mass action expression. 5.29 times 10 to the minus fifth equals x times x over 0.100 minus x. If you algebraically fold this out, you're going to end up with the quadratic equation, 0 equals x squared minus 5.29 times 10 to the minus fifth x, plus 5.29 times 10 to the negative fifth x, minus 5.29 times 10 to the minus 6. If you plug all this into the quadratic equation, I'm not going to go through all those steps here, you will get that x equals 2.28 times 10 to the minus third. The other value is negative and would not work for this particular calculation. So we're going to, this x value, this is important to note, this equals the hydroxide concentration we're looking for. So now, part one, achieved. The hydroxide is 2.28 times 10 to the minus third molar. Now we can use this to calculate our percent ionization. Remember that percent ionization is equal to the concentration of hydroxide at equilibrium over the concentration of ammonia initially. And the ammonia concentration is given in the start of the problem. We just calculated OH minus. All we have to do is plug in the numbers. 2.28 times 10 to the minus third over 0.100. Oh, and this is supposed to be times 100% because we're talking about percents. Times 100%. Crunch out your numbers and you get that this is currently 2.28% ionized. And there you go. So to recap, if you run into one of these problems again, you're going to start by using the ice table to get the hydroxide or the hydronium concentration that you need, and then you'll use that hydroxide or hydronium concentration to calculate the percent ionization. I hope that cleared things up. I will see you guys after spring break.